We might not notice, but tremendous technology and mind-boggling science constantly surround us in the products we use every day. Behind their practical use lurk hidden histories, dramatic discoveries, and awesome experiments. They are wicked inventions. Coming up, life rafts, the connection between the Titanic disaster and safety at sea. The battery, the electrifying science behind the devices that are powering today's gadgets. Chandeliers, the fascinating story of the very definition of luxurious lighting. We reveal the surprising science and amazing manufacture behind these wicked inventions. Today we take our safety at sea for granted, confident in the capabilities of the boat we are on and reassured that a life raft will be available in the unlikely event of an emergency. But this hasn't always been the case. In the long history of seafaring, the idea of a dedicated emergency craft was not considered, with a ship's small boat the only real option of an escape in an emergency. It wasn't until the turn of the 20th century, with the huge increase in the numbers of passengers travelling on board steamships, that the problem of their safety was given any serious consideration. The famous Titanic disaster of 1912 highlighted the danger faced by travellers at sea.
So if we take the Titanic, for example, its lifeboat capacity was around 1,000 people, whereas the potential capacity of the ship in its entirety was 3 times this much, which really showed that the maritime safety legislation needed to be updated.
Following this tragic event, SOLAS, the International Convention for the Safety of Life at Sea, ruled that at no time of its voyage may a ship have a total number of persons than that for whom accommodation is provided in lifeboats. This still stands today, ensuring the highest level of safety. The big problem for ship designers was that these lifeboats took up an enormous amount of space on deck. To solve this problem, collapsible lifeboats were designed, and in 1932, a huge leap forward in space saving was achieved with the development of the world's first inflatable life raft. The chances of survival at sea were greatly increased if you had a craft that could float, but exposure to the elements could be just as dangerous as the sea itself. The experience of the men unfortunate enough to find themselves adrift in the icy waters of the Arctic convoys in World War II added the requirement of a protective cover to a life raft's successful design.
During the Battle of the Atlantic, lots of boats were being torpedoed, and that was forcing men to jump into freezing cold water with very little chance of survival. So that required a purpose-built lifeboat to be designed, which could protect these men from the elements, and that forms the basis of the modern lifeboat that we have today.
Since their development, life rafts can be credited with saving the lives of thousands of people, with amazing stories of survival testament to their importance at sea. They may be an essential emergency item, but how are life rafts made? Modern-day life rafts really have come a long way since the cumbersome boats of yesteryear, and we're going to discover how the perfect fold can increase your chances of survival. At their facilities in Denmark, Viking life-saving equipment produce some of the most modern and widely used rafts today.
We have produced a lot of life raft over the years since 1960. We know our life rafts have been used in emergencies. We are in contact with people who have been rescued by our products, and are of course very happy that in the situation where they needed it the most, they had a product that worked to the fullest and who saved their life.
The Viking Rescue Pro Life Raft is an efficient, last resort means of evacuation, intended for use by people on board yachts in the case of an emergency caused by fire or sinking. Once launched and inflated, the life raft provides good shelter, protection, and all the necessary survival equipment to keep evacuees alive until rescue arrives.
Everyone who works with the life raft know that what they do can eventually mean that it will be saving somebody else's life.
The materials used for a modern-day life raft must be of the highest standard to ensure the safety of passengers in an emergency. Because of this, a life raft's production begins with testing the raw materials of natural rubber and canvas before they can be used. A tensile testing machine is used to test the strength of the materials by stretching it with great pressure. This then records the pressures used, and with this data we can see at what point the materials will break and how much they are able to stretch. With the materials now tested, the next stage is design. Using computer-aided design or CAD software, raft engineers can hone their designs ready to be put in production. The designers must include key features, including self-righting abilities and 2 large entry points, meaning that it can be boarded within seconds. From here, the designs are sent to a cutting machine. The materials that have been tested are laid out onto a large cutting table, where the machine will then cut it to the exact specifications of the design. Another clever little trick by the machine is to lay out and cut all of the segments of the raft in the most efficient manner possible, keeping wastage to a minimum. Once the materials have been cut to shape and size, the canopy of the life raft is sewn together, using traditional sewing machine techniques. This very hands-on approach means that each operator sewing is able to consistently check their work and the materials throughout, making it extremely accurate and minimizing any faults. Of course, this little raft is going to need to stay afloat. The next stage of production is to glue together the tubular modules of the life raft that will inflate and give the raft its all-important buoyancy. Highly trained technicians precisely glue each piece together using an extremely high-strength, water-resistant adhesive. Now that the tubular modules have been glued firmly together, it is vital that they are tested for any leakages that may prove fatal if and when the life raft is ever needed. The modules are inflated with double the required working pressure. They are then left for half an hour, where the inflated modules can be analysed for any air leaks. Because double the pressure is used, the technicians can be confident that if there are no leakages at this point, the life raft will be stable when called into action. Our life raft is really coming together now. We're at the assembly stage, where the bottom, ballast bags and canopy can be assembled onto the inflated rubber modules. Again, this process relies on manual craftsmanship and precision. Once the raft has finally been assembled, the all-important emergency kit of the life raft is fitted. The contents of this kit include flashlights, batteries, parachute rocket signals, drinking water, first aid kits, instructions for use, and many more vital components that will give those passengers in need their best chance of survival. With the life raft complete, it is time for it to be packaged. The life raft, complete with emergency kit, is compressed and packed into a compact and sturdy fiberglass container. It is vital that the life raft is creased, folded and rolled in exactly the right way so that it's guaranteed to deploy properly if needed. It's amazing how compact the life raft can be made so that it takes up minimal space on deck. This means that multiple life rafts can be stored on ships so that every passenger has a chance in the event of an emergency. Once the life raft is finished, it is time to be tested on the open waters.
I think that's something to be proud of every day when you go to work, that what we do can save lives.
With its ability to inflate almost instantly and be stored without taking up too much space, this modern life raft truly is a wicked, life-saving invention. With the modern world addicted to mobile technology, we seem to spend most of our lives looking for places to charge our devices. From laptops to mobile phones, the piece of tech powering your gadget is surprisingly old. It is, of course, the battery, and we're going to find out how plaster of Paris help make them truly mobile. In simple terms, a battery converts potential chemical energy of a material into electrical energy via reactions. The term battery was actually used before they were even invented. Benjamin Franklin adopted this military term used for a collection of cannons when combining multiple Leyden jars together in 1748. The jars may have stored static electricity, but they were not a true battery as they discharged all of their power in one instant. Fast forward to 1800 and Italian Alessandro Volta would be the creator of the world's first modern battery.
He took discs of copper and zinc and stacked them and had a wet rag between them which contained a salt medium, essentially salt and water together. And the electrical potential between the two metals allowed current to flow. And as he made a large stack of these,
The voltage, which is named after, added up, and he could actually generate a rather large current because they were quite big disks, as well as a large voltage because there were many of them stacked together in series.
Volta believed he had created a source of never-ending power, which was not quite the case, but his battery could last up to an hour. Following on from Volta's voltaic pile, the battery was rapidly developed through the 1800s and was a major factor in powering the ever-expanding telegraph networks. But how does a battery actually work?
An electrochemical battery works by exploiting the difference in electrical potential between two metals. We may think of metals as being metals and they both conduct electricity, but they have different, what's called an affinity or desire for electrons. So zinc will have more of a desire to hold onto electrons than will copper. And when you can exploit the fact that they're different by putting some kind of medium in between which allows ions to be transported, it has to be so often water with salts added. That allows the current to flow. What you have to then be able to do is be able to turn it on and turn it off. If you have two electrodes, one's the anode and one's the cathode, and you hook up wires to them, what will happen is you'll have the ions that you will want flowing from one electrode to another. So one electrode degrades, whereas another one gets reoxidized. Then the electrons flow through the wires back around to the other side in order to allow the chemical reaction to complete at one end versus the other. So you actually have a flow of ions through the medium, and you have electrons flowing through the rest of the system.
So, the world had battery power, but these early models would have been no use for our mobile phones. They were big and bulky and fitted with rather nasty liquid chemicals that could give off poisonous fumes and sometimes needed topping up. These wet cell batteries could also leak, and often being made of glass were very fragile and needed to be kept upright and not moved about. Hardly mobile then, but a major mobile leap forward was made in 1896 when a German called Karl Gassner replaced a liquid electrolyte with a paste made of ammonium chloride and plaster of Paris to create a sealed battery, which required no maintenance and could be used in any orientation. The dry cell battery was born.
Dry cell battery sits with the electrodes separated, and the electrolyte doesn't exist, but it actually takes in water from the atmosphere, and that water from the atmosphere is used over time to allow a slow current to trickle. So dry cell batteries tend to be for powering systems over a long period of time, whereas wet cell batteries tend to be lots of power in a short space of time relative to that of a dry cell battery. Dry cell batteries have a relatively long shelf life because they need water in the atmosphere, and if they're appropriately sealed, they will last quite a while before they degrade. Whereas wet cell batteries will have a lifetime that's in the course of years, but are slowly losing battery power because they're slowly reacting nonetheless.
Today, the type of dry cell battery you might pop into your flashlight will typically be a zinc carbon design. The cell is made up of an outer zinc container, which acts as the anode. The cathode is a central carbon rod surrounded by a mixture of carbon and manganese dioxide. The electrolyte is a paste of ammonium chloride. A fibrous fabric separates the two electrodes, and a brass cap in the center of the cell conducts electricity to the outside circuit. While dry cells might have meant more mobile power, they were too puny in output for laptop and mobile phone use. The power source that arguably created the mobile digital revolution was the invention of the rechargeable lithium-ion battery in the 1990s. As lithium is the metal with the lowest density and with the greatest electrochemical potential and energy-to-weight ratio, it meant that batteries could be designed that were smaller, lighter, and were even more powerful than ever before.
In the space of where you may have had one ion, you can have two or three. And so your energy density is tripled or more. And that's why you want a lithium-ion battery. The energy density and the ability that they can actually be rechargeable, because you can move them back from lithium ions to lithium metal, lithium ion to lithium metal, and they don't suffer as badly with recharge cycles destroying the lifetime of a battery. Older batteries, nickel-cadmium batteries, often after about 1,000 charges, they're gone. There's no useful lifeness in them. Lithium-ion batteries, by contrast, can often last a lot longer and deliver more power and be smaller.
So, next time you switch on your mobile phone, just remember the amazing little power unit that lurks inside. The battery, truly a wicked invention. Can we create a battery just using coins? we're going to need 10 clean copper coins, 2 wires with crocodile clips, a multimeter, some card, aluminium foil, electrical tape, and some vinegar. Take the card and draw round one of the coins 9 times. Next, we cut out the card shapes to create 9 discs and place them in a bowl of vinegar. We take a sheet of foil and create another 9 discs. We place a coin onto the work surface and add a vinegar-soaked card disc and then one of the foil pieces. We repeat the process until we have used up all the copper coins, with the final copper coin being placed on the top. Fix the wires to the stack and we are ready to go. We connect the wires to the multimeter and we can see that our pile of coins is producing an electrical current. We have basically created a model of Alessandro Volta's voltaic pile. As we've seen, a battery produces electricity via a chemical reaction when 2 different metals come in contact via an electrolyte. In our case, the metal in the coins and the aluminium foil are the metals, and the vinegar-soaked card acts as the electrolyte, facilitating the travel of electrons, which creates the electrical current in the wires. Can we create a battery just using coins? Yes, we can. Wicked challenge smashed. There are few decorative items that show off status and wealth, quite like a glistening chandelier. But did you know that it has something in common with an elephant? These ornate light fixtures have adorned the homes of the wealthy since medieval times, with their familiar ring or crown-shaped designs acting as a symbol of success.
You had to be very wealthy to have anything like this. Again, because candles are expensive and most people would have got by with sort of 1 or 2 candles on their bench, but to have a whole chandelier with numerous lights on it or candles, this is how it developed, and only the wealthy would have had such a thing.
The word chandelier comes from the Latin word candelabrum and were traditionally lit up by the candles, with the earliest references coming from medieval times. Chandeliers grew in popularity with royalty and the wealthy, and by the 18th century could be found in all of the finest mansions, manors, palaces and castles in Europe. The crystal chandeliers that we are most familiar with today were made possible by advances in glass making, mainly by Venetian masters.
So rock crystal was the next development in chandeliers. Again, it was still very wealthy. And rock crystal, it was a form of quartz and it reflected light. So it all helped to diffuse light in a room, and especially a large room. If you're imagining a chandelier hanging from a large hall or large room in a palace, this helped to bring more light.
These fantastic glass ornaments would light up rooms in a new and unique way as the light bounced from the glass. Murano in Venice, Italy, became famous for its glassmaking due to the popularity of their beautiful and much sought-after chandeliers. By the mid-19th century, gas lighting caught on and many of the original candle chandeliers were converted. These were often called gasoliers, although the name never stuck. Of course, the introduction of electricity by the late 19th century meant that this became the power source of choice for many chandeliers. The largest crystal chandelier today can be found in the Dolmabahce Palace in Istanbul. It has 750 lamps and weighs an amazing 4.5 tons. That's as heavy as an elephant. So, just how are these amazing creations made? We've just seen how far back the history of the chandelier goes. But did you know just how long the highly skilled glass cutters that make these spectacles of light have to train to achieve perfection in their work? Wilkinson plc are specialists in recreating and refurbishing chandeliers from the 18th and 19th centuries, and even hold a royal warrant from the Queen of England to do so.
When my grandfather started the business, he was a modern glass cutter. He cut wine glasses and decanters and vases. And over the years, it developed into making more and more pieces for chandeliers. And eventually, we decided to make complete chandeliers of our own.
To begin the process, glass is delivered from highly trained glass blowers.
We're not big enough to melt our own glass. We use a very specialised glass blower in the south of England, and he's very good at producing just one piece exactly the same as the piece that we want.
Once the glass has been delivered, the first step is to make cuts in the lead glass with a carborundum grinding stone. This creates the shape that is required for each piece of crystal. This step is very risky, as cracks can occur if the glass is ground too thin. Because of this, it takes an immense amount of accuracy and skill from the glass cutters.
Depending on the chandelier, it takes maybe anything from a month to 12 months to make a chandelier complete. The glass cutting process is the most lengthy and most difficult.
To reduce the risks of cracks even more and to also aid with grip, the glass cutters sometimes use modelling clay. There is a constant flow of water which runs onto the wheels. This aids the cutting process by keeping the temperature of the glass cool, as well as avoiding friction caused by overheating the glass. After this, the grinding stone is changed to a sandstone. This smooths out the rough cuts that have been made by the carborundum stone. Depending on the size and complexity of the glass crystal that is being cut, it can sometimes take more than a day to achieve. Although electronic machines are used, the cutting process relies heavily in the person offering up the glass to the wheel by hand. Apart from the electricity powering the stones, this method of glass cutting has not changed for hundreds of years.
Victorian chandeliers were cut with a mitre wheel, which is sort of this shape, and so you would cut a V into the piece of glass in one go. The Georgian style of cutting was done with flat wheels, and to get a V you cut this side first and then this side, so it was a shallower cut. And when you're making a really fine reproduction, there is no other way of making this flat cutting without doing it the same way that they used to in Georgian times.
The crystal glass then needs to be polished. To achieve this, a cork wheel is rotated on a spindle. A soft sponge is then used to add a water and pumice mix to the cork before the crystal is polished. In order for the crystal to have the bright shine that is to be expected of any good chandelier, the crystal is polished a second time. Here, a water and rouge mix is added to the wheel with a sponge, and then the crystal piece of glass is polished on this.
We take all of our staff on as trainees. Probably after about 7 years, they really are very skilled and are able to cut and polish just about anything we ask them to do.
Here, a solid rod is drilled to create a tube. This tube will act as a spacer that ensures that the glass bears no weight from the other pieces and avoids it being crushed. It also gives the chandelier a brilliant brass finish by hiding any unsightly parts. Washers are also cut and smoothed that will hold the glass pieces in place and stop them from wobbling. Decorative brass parts are also prepared that will serve to improve the look of the chandelier. To complete the chandelier, it is hung in order for the freshly cut crystal ball to be installed, as well as the glass drops. And there we have it, a beautiful, glistening chandelier, steeped in history and still as eye-catching as they were centuries ago. The chandelier, truly a wicked invention. So, there you have it, a dash through the hidden history, super science and amazing manufacture of products that you use every day but have never realised their amazing backgrounds. Life rafts, the battery, and chandeliers. All wicked inventions.